Hello, my name is Luke, and welcome to this series on reinforcement learning. So this is part 2 of the reinforcement learning basics videos. So if you haven't seen part 1, go check out that one first, where we went through some of the basic concepts of reinforcement learning and introduced some simple reinforcement learning algorithms, and left off at the point where we said, up until now, we are using this state transition table, this state action table that modeled the environment in order to work out what actions we should take. And we said, firstly, is that reasonable to expect that we would have this state transition table, this model of the environment? What if, we're in an environment or a situation where the state transition table is complicated and we might not even have it? So, furthermore, if you remember way back, when we said that we can sort of model the process of our trajectories as a Markov decision process, I said that that p-value, that probability that taking an action will get us from one state to another, we said that was 1. So we said that our environment was deterministic. We would always get from one state to another when we took this action and we knew what it would be. So not only did we have this model of the environment, it was deterministic and we knew exactly where we were going to go. Certain environments that might be deterministic and fully observable, so we know exactly what the model is and it's deterministic. If you're playing a game of checkers or chess, that would be one such situation. The environment or the possible states might be very large, but you could use those methods we saw if you had that complete model of the environment. However, in many environments, in many situations, you either don't know, or maybe it's too complicated to fully model the environment, even though you potentially could, and so you don't want to. So if we don't have this model of our environment, what can we do? Well, that brings us to a class of RL algorithms called model-free learning. Okay, so one algorithm we're going to look at first is called Q-learning. So if we don't have this state transition table, then our policy cannot be to check what the next state is going to be if I take a certain action and see what the value is. So what we need to do is we need some other way of determining what action we should take. If we don't know what the next state's going to be, then we need to instead assign value to the actions that we take themselves. If we had some way of assigning value to the actions, then we could say, let's just pick the action that has the highest value. I don't know what state that's going to take me into, but through the learning process that we'll look into in a moment, I know that this is the best action to take. So I don't know what state I'm going to be in next, but through experience, through taking actions, I know what value states or what the value of the states were if I took this action. But I don't know for certain that this action will take me into those states. But from experience, I know what they were. So I still had my trajectories, I have my rollouts. I know what happened in this situation, or in this instance. I took this action, I got to this state, this state, this state, this state, got the reward, but there's no guarantee that's always going to happen. So I can't use that information. You could potentially use that information if you tried to learn the model, but we're going to assume that we're not going to learn it. But through those experiences, we can assign or learn some value for the action itself. So in Q-learning, that's what we do. So instead of a value, we sort of call it a quality. So each action or each state action pair has a Q value. So that Q value is going to change for a given action depending on what state it is. Certain states, certain actions are going to be good. Maybe one action is really good in this state, but that action might be not so good in a different state. So the Q value is for a state and action pair. Okay, so how do we learn this Q value? So similar to the value function, we're going to have some, in our grid world, we're going to have some table, which is our Q value table. And we're going to initialize that to all zeros and then update it from there. So what is the update step for our Q-learning, our basic Q-learning? Well, you can see we're using temporal difference learning again, with a slight difference. So the Q value for a state action pair is going to be the current Q value plus alpha, which is our learning rate, times the reward we got for taking this action in this state, plus gamma, that's our discount factor, times the maximum Q value in the next state we were in our trajectory. Subtract the current Q value. So you can see it's very similar to the normal temporal difference we saw where we did our value function update. So what is this max Q value here? So we did our trajectory, we did our rollout. I'm now updating the Q value for this state action. We look at the Q value distribution of all the actions, Q values for the actions in the next state in that trajectory, and we pick the one that was the highest, and we use that to update the current Q value. So what are we saying here? So what is this update step doing? Well, it's saying that the Q value for my any given state action is the value that is saying that it's the value of this action is, if I take this action, how good does it get from here? So it's not just the value of taking this action and getting the immediate reward. It's saying I took this action, how good can it get from here? Because I'm taking into consideration the max Q value of the next state. That next state is taking the max Q value from the next states, etc., etc. So this Q value tries to represent the action value of a completely optimal agent. So it tries to learn this action values of an agent that is always taking the best possible actions. Well, the best possible action is going to be the one with the highest Q value. You might think, well, why are we taking the max Q value? Doesn't it kind of make more sense if I just take the Q value of the action I actually took in that next step? And you can do that. It's known as the SASA algorithm, state, action, reward, state, action. So state action of my current state action, the reward, and then the state action of my next state action. And you can update it that way. But this particular permutation of Q learning is trying to represent an optimal agent. If I can learn the Q value of an optimal agent, then I can become the optimal agent. So hopefully that makes a bit of sense. So as I said, we need to learn this Q value table now. So we don't need the state transition table for our policy. We don't need the value function. All we need is this Q value table. So for every state, I'm going to have a value for each action, and the value is going to be different for a given action depending on what state I'm in, and we'll initialize this all to zeros. Okay, so our policy, we're going to use the epsilon greedy policy. We saw at the end of the last video how we have this trade-off between exploration and exploitation of the knowledge that we've gained, and we want to use some of that knowledge during training to learn or to get to the reward more quickly so that we can converge faster. So we're going to use epsilon greedy again for our Q learning. The only difference here is that we're not using the state transition table to decide what action to take. All we're going to do is we're going to get our state transition table. Sorry, not our state transition table, our Q value table. We're going to look at what state we're in, and we're going to take the action that has the highest Q value. Okay, so let's have a look at a code example of that. So the environment and the reward function is the same as last time. We have those negative rewards, those states we want to avoid. And I've set epsilon a bit higher than last time as well. So there's my reward. So we still need the state transition table because this is the model of the environment. We want to simulate the world, so we need it to know what the actual next state was, but our policy never uses it. We never actually use this state transition table when deciding what action to take. So the Q value update is very similar to the value function update using temporal difference learning that we saw before, except of course that next value is not the next value, it's the Q value, the max Q value of the next state, and we're updating it in a similar way, right? The only difference is that, again, we're just taking the max Q value of the next state instead of the actual next value. So the test agent function, again, is very similar, except deciding on what action to take. You'll note here that we're not using the state transition table. If I go back to the epsilon greedy code, you can see when we decide what action to take, we need the state transition table. We put the state in the state transition table, we get the possible values from the state values, and we take the action that has the highest associated value. But we don't need that anymore. Okay, so let's give this a go. Let's give it a train and see how we go. So it should train pretty quickly. And let's have a look at the Q value table. So you can see it's much bigger than the value table or that we had before. So every row here represents a different state, and each column represents a different action. So you can see we start at state 12, so state 0 here. You see we have the highest action here, so we've got, oh, can't remember what that is. That might be go up, go up, go up, go up. And then, yeah, so you can sort of follow along what it sort of worked out what to do here. So you can see a lot of states we actually don't really visit that often. Maybe my epsilon isn't right. Maybe I need to take more random actions. But if we look at our score log, there we go. We get to the optimal, so an optimal policy of getting 10 all the time. Though we aren't taking into consideration how many steps it took, as long as it didn't hit the timeout. So maybe there's more optimal policy. But we can see that, yeah, we're going up, going up, going up, and then going right, 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 then up. Cool, very good. So you can see that we've learnt the policy pretty quickly. You can see it took about the same amount of time as the TD learning, the value learning. But again, crucially, we don't have, or we don't rely on that state transition table that defines the environment, the model of the environment. What that means is that you could use this algorithm in a situation where you may not know what the actual model of the environment is. If you come up with some way to potentially discretize some data from the real world, maybe some sensor data, you have a bunch of sensors, you can sort of chunk up the continuous values of those sensors, and maybe you have some actions that you could take. If you could build some discrete number of states and discrete number of actions, then you could just plug it in to this Q learning algorithm. Here we need the state transition table because we've defined the environment, but if the environment is the real world, you don't need this. And if you chunk it up in some way, you could learn to take actions and try to learn some optimal policy. So even though this grid world is, very constructed, it's a bit of a toy example, you can use what we've seen so far to learn to act in the real world. As long as you, constrain the environment in some way, because we're using a discrete number of states. Once we get onto deep learning, then we don't have to worry about discrete numbers of states. But for now, don't think what you're learning can't be used in the real world. It can be. Okay, so Q learning is an example of value-based learning. So it's a similar class of the other value-based learnings we saw in the first video. But again, it's a model-free value-based learning method. We don't need the model of the environment. However, the policy that we use in these value-based learning methods is defined by us. So the policy that we're using in Q learning there was the epsilon greedy policy. While the Q value does inform the policy on what actions we should take, the policy still is the epsilon greedy policy. So value-based learning, we learn some values, some value functions, some value table, and that value is then used to inform the policy, the epsilon greedy policy, for deciding what action to take. There are different policies you could use other than epsilon greedy, but depending on the situation, use different ones. But how do you know which one might be optimal? Well, maybe try them out. Maybe different environments, different policies are better. But wouldn't it be better if we could in some way, or alternatively, learn the policy directly? So instead of deciding on some policy and then learning some Q values or some values, how about we get our model to create the policy directly? So That leads us on to policy-based learning. So instead of learning some intermediate value or Q value that then informs the policy that we define, how about we learn the policy directly? So how does this work? Well, in policy-based learning, we aim to try and learn some probability distribution over possible actions, and then we randomly sample from that distribution to get the action directly. So our model outputs some distribution of actions, we randomly sample, and we get an action directly. So our model directly gives us, after random sampling, the action that we should take. There's no intermediate step of some value, some key value, and then plugging that into a policy, right? Okay. So what we get from that is some action probability table. So looks a bit similar to our Q value table. For every state, we have some probability distribution. In our discrete case, we're going to use a discrete categorical distribution. So every action is going to have some probability that we should take this action in this state. Again, that should all add up to 1. And then what we do is we just randomly sample from this distribution to get our action. Normally we work with log probabilities instead of probabilities or logits. And usually we work with, or we're going to work with in our examples, unnormalized log probabilities. So our table, the probability values won't actually represent a valid distribution, but we're going to use softmax them, and then sample from that when we want to take our actions, right? And we do that because it's just easier to keep track of and manage, right? And that's pretty standard to do. So each probability kind of tells us how likely is this action the best one to take, right? And if the environment is deterministic, well then that probability might go pretty close to 1. But if it's not deterministic and there's some unknown or unseen states or unseen actions that's occurring in the world, well, maybe 2 different actions might be good, right? Maybe take one time, maybe take another, because we don't have full information of the environment, right? It also means that we don't need a state transition table, right? I don't need to know what the environment is doing to know what action to take. I just sample from my distribution and get my action directly. Okay, so how do we learn these probabilities? So the probability update for our very basic policy-based learning is very, very simple. So we define or calculate some quantity called the advantage, and we simply say our current log probability, unnormalized log probability, is equal to current probability plus some alpha, some learning rate times the advantage. So if the advantage is positive, that means we've done something good, we'll increase the probability. If alpha is negative, because we've done something bad, we'll decrease the probability. So increase or decrease the probability based on if we've done something good or done something bad. And it's simple as that. The advantage doesn't necessarily need to be negative sometimes. It can be always positive. Let's go back. Even if it's always positive, because we've got these unnormalized log probabilities, once we do the softmax, if we're always increasing one particular action, once we normalize, we'll decrease the probability of the other actions. So even if it's always positive, it doesn't really matter. So the first algorithm we're going to look at for our policy-based methods is reinforce, or version of reinforce, where the advantage is just going to be the returns. So we're seeing what the returns are, our cumulative discounted rewards are our returns. In our example, we do have positive and negative rewards, but as I said, even if the returns are always positive, this will still work because we'll normalize. So that update step for our probabilities is just simply the current probability or current log probability plus alpha times the returns that we calculated. So let's have a look at an example in the code. So I'll go to our reinforce. So you can see I've increased the value of the negative rewards. I find it converges a bit better, quite a bit better, if the magnitude of those is a bit higher. The hyperparameters, the gammas, the alphas, the reward magnitudes, quite a bit different, tend to be quite a bit different between the value-based and the policy-based learning. That's fine because you have control over that. But yeah, just to be something aware of. So the sort of layout of the rewards is the same. We still need the state transition table to model our environment. We've got a returns calculation here, same as before. So you can see our test agent, again, very similar, but we've got this difference line of code here when deciding what action to take. So you can see we take our state action log probabilities or unnormalized probabilities, which we initialize to random numbers at the start. And we get the current state, we get the distribution of the actions, and then we do our softmax. If you're not familiar with the softmax function here, basically, I won't go into too much detail, but it's a way of making sure all the values are between 0 and 1 and also sum up to be 1. So a valid categorical distribution. So that's all we're doing, what we're using the softmax for. We're not updating the actual probability table. We're keeping that as the unnormalized probability so we can add or subtract values from that, and then we're only normalizing it once we need to actually take the action. So we got our valid distribution, and then I'm using NumPy random multinomial to then sample from that distribution. This returns a one hot-coded vector for some reason, with a 1 in the location of the action it sampled, or the value it sampled, and zeros everywhere else. So to extract the actual index of that action, I just do an argmax, and that gives us the action. Okay, so you can see we don't have epsilon greedy in our training loop to select the actions like we did with Q value. All we're doing is randomly sampling from the distribution, right? At the start, we've got random actions, and we're randomly sampling from a random distribution, so we'll have random actions. So that allows us to do our exploration. But as we start to learn what actions are better than others, we do more exploitation of what we've learned. You can do a similar thing in the Q learning and value-based learning, where you start with quite a high epsilon. So an epsilon where we're taking a lot more random actions, and then slowly bring the value of epsilon down so we exploit some more. So you can do that as well. But that sort of implicitly happens with our policy-based learning. So let's run that. I'm doing a few more steps here because the learning process is a bit more random. And you'll see that the score log for our reinforce isn't that great. We do eventually learn to get there, but we haven't actually converged to the best outcome. If I run this whole code again, we might get there. But you can see we have a few problems. One issue with the current implementation is that, you may have guessed, if I'm always adding or always subtracting values from this table, well, if I'm taking the same action over and over again, the value of the log probability for a particular action in a particular state might get quite large, and I might converge to taking the same action every time before I work out what to do next. So what that means is I'm not doing enough exploration early on, and I've converged to taking the same action too quickly. One thing that you can do is constrain the values of those log probabilities or unnormalized probabilities in some way so that they don't sort of blow out too much. So simplest form is to just clip them between some range, -5 to 5, so they can't get larger than that. Actually, let's have a look. The maximum log probability is 48, so it's quite large, right? It's unlikely that I'll be taking any of the other actions. So you can see the probabilities here. So this is the normalized probability, so 1, 1, 1, 1, 1. I'm never going to take any other action than these ones here. And if that happens too early on, as I said, we won't do enough exploration, and as we know, that's very important. So let's try this with the clipping. Hopefully it works out. Oh, there we go. So I think that's converged to around 10 there. You can see it's still pretty noisy. Note that it's noisy here because during testing, we're still doing random sampling of our action distribution. In the Q learning, the other learnings, we're not doing any random sampling. If we were doing epsilon greedy during testing, we would expect to see a bit more noise. So that's really the only difference. So it's not a fair comparison directly to each other, but there you go. And there you go. So we converge nicely to getting the reward state and avoiding the negative states. So you can see how clipping, in this case, for our policy methods, allows us to explore a bit more than we potentially would have otherwise. And we'll look at another method of doing a similar thing in a moment. So there we go. Our policy-based methods, we've learnt our policy directly, we've randomly sampled our actions, and we've learnt to act in our environment. So you don't have to just have a categorical distribution there. You can have a normal distribution, in which case it looks a bit different, the update. So when we get to deep learning, we might look at how to use normal distributions instead for a continuous action space. Okay, so can we do any better than reinforce? Well, yes, we can. So actor-critic methods are policy-based methods, but they sort of mix value learning with policy learning. So all we're doing here is trying to work out a better way of calculating some advantage, a better advantage, right, than just the returns. So in actor-critic methods, what we do is we look at the difference between the current returns, or the calculated returns for a particular trajectory, and the learnt value function. So our advantage now becomes the returns subtract the advantage, right? And this now becomes much more like what we sort of described the advantage as. Our advantage is supposed to tell us when we've done good or when we've done bad. By subtracting the returns from the value, what we're saying is, was this trajectory better than average? So the value function tells us what the average returns are, if we remember back to the first video. So by subtracting the returns of the current trajectory from the value of the average returns, which is our value function, our advantage represents how much better or worse we did than average with our current trajectory, or with our trajectory. So if the advantage is positive, we performed better than average, and so increase the probability of taking that action. If we got a negative advantage, we performed worse than average, and so decrease the probability. So the update step is exactly the same. It's just what the advantage is has changed. What that means is we now also need to learn a value function as well. But our policy is still directly learnt, or directly produced by our model. So let's have a look at our actor-critic learning. So pretty much everything else is the same. We need to calculate our returns, but we also need to learn a value function as well, and we're going to use temporal difference learning. You could use any of the other value learning methods we saw previously, but as we saw, TD learning gives us the best of the stability with a bit of bias. But so we're going to use that. The testing is the same. We do the exact same random sampling once we've got our action probabilities. And our learning, again, is very similar, but we do a TD update to get our values. Same what we were seeing before. Calculate the returns, same as what we did in reinforce, but the advantage is now just the returns, subtract the values, and then we use that, same as before, to update the probabilities. So let's run this all. So there we go, we've got our probabilities, and there we go. So we've converged a bit nicer, a bit less random at the end, and we've converged a bit better. So a bit of an improvement. In more complicated environments, the improvement is quite a bit more significant. You'll have to trust me on that, but we'll see that potentially a bit later on. So one of the last things I want to show you is just a different way of making sure that the probabilities don't blow out. As I talked about before, I was just clipping them before, but another way to constrain them is to add a little penalty on the magnitude of the log probabilities. So every loop, what we do is we also reduce the magnitude. So subtract equal some very small scaled value of the current probabilities. So if they're negative, we're going to add a bit. If they're positive, we're going to subtract a bit. What this does is just sort of squishes the distribution to make it a bit more flat. So we're increasing the entropy of the distribution so that the distribution is flatter, and that means we'll take more random actions. So let's train with this. So it's just a different way of making sure that the distribution is not, we're not taking too many of the same actions. We're not converging to taking the same action over and over again. You know what I mean? And there you go. So that small change has meant that we've converged a lot quicker and it's a lot more stable during our score rollouts. And again, the comparison is not really fair because we're sort of taking random actions during testing. Taking random actions during testing might actually be ideal because there may be certain situations, as I kind of hinted at before, where something's happened in the environment that we're unaware of, that we're not able to observe. And so we might want to oscillate between taking two different actions, testing out different possibilities, even though the state, from what we can tell, is exactly the same. And if I'm only doing greedy actions, taking the same action, then I might get stuck. But trying random actions during testing, during actual inference, might be good. So something to think about. Okay, so that's it for this video and this first part of reinforcement learning basics. So as I kind of discussed a little bit, if you have some way of discretizing the real world, which is sort of continuous, you could use these algorithms, construct them as a sort of grid world. And if you're using the model-free learning algorithms, the Q-learning and the policy gradient algorithms we saw, you could learn in the real world. But again, that requires you to discretize the world. It requires you to know something about the world, make sure you made sensible choices on how to chop up the world into those discrete states. So maybe you just want to use the full continuous spectrum of the real world. Well, for that, we can't use little tables. We need some continuous function. And for that, we can use deep learning. As I mentioned at the start of the first video, if you're unfamiliar with Pytorch and deep learning, I have a whole series on Pytorch deep learning. So you can go through that if you're unfamiliar. But now the next two-part series, potentially 2 parts, is going to be on deep reinforcement learning. So using the ideas of reinforcement learning, but now throwing away that table, the discrete table, and using a neural network instead, and seeing what that gives us and the sort of slight changes we need to do to the existing algorithms we've already seen in order to get them working with deep neural networks. Okay, that's all I've got for this video, and I'll catch you in the next one.